Alright, we're going to continue talking about concavity and the second derivative test today, or in this video. And we discussed concavity in our last video. We did one really long example. Today, or not today, in this video, we're going to focus on points of inflection. Now, we're going to first define points of inflection. So this is a mathematical definition. We're going to say let f be a function that is continuous on an open interval, and we're going to let c be a point in the interval if the graph of f has a tangent line at the point c f of c, then this point is a point of inflection of the graph of f when the concavity of f changes from up to down or from down to up at that point. So basically a point of inflection is the point where we change from going down to up or from going up to down. In a way, it's kind of like a max or a min. So I've got a theorem, theorem 3.8, on points of inflection. We're going to say if the point c f of c is a point of inflection of the graph of f, then either f double prime of c is equal to 0, or f double prime at c does not exist. So the second derivative at a point of inflection is going to either be 0 or it doesn't exist. So let's actually go and look at another example. We'll call this one example 2. We're going to determine the points of inflection and concavity of the function f of x equals x to the fourth minus 4x to the third. So the first thing we're going to do is we're going to try to figure out the second derivative, and in order to do that we need to first figure out the first derivative. So f prime is going to equal 4x cubed minus 12x squared. Now we can go and figure out our second derivative now that we've got the first. So f double prime is going to be 12x squared minus 24x, and we can leave it that way. I'm also going to write an equivalent form of that because we're going to set this equal to 0. So I'm going to end up factoring this. In fact, I'll just do that right now. I'll do the whole process. We've got 12x squared minus 24x. We're going to set it to 0. Both terms have a 12 and an x in common, so we're going to take that out. 12x times x minus 2 is equal to 0, and we set each factor to 0. So 12x equals 0, and x minus 2 equals 0. Well, the only way for 12x to equal 0 is if x equals 0 itself. And the only way for x minus 2 to equal 0 is if x is 2. So these are our inflection points which was part of what we had to do. We need to determine the points of inflection, but we also need to determine the concavity. So we can use these inflection points to help us determine our intervals. So the intervals we're going to look at are from negative infinity to 0, from 0 to 2, and from 2 to infinity. So that means we are going to test or pick a value in those intervals to test for concavity. So we're going to find the second derivative at negative 1. We can find the second derivative at 1 and at 3. So we're going to plug those values into our second derivative. Now if I plug negative 1 in, what we're going to get is 36, which that is a value that's greater than 0. So in this interval, we are concave up. So from negative infinity to 0, we're concave up. If I plug 1 in to my second derivative, I get negative 12. And since that value is less than 0, on that interval, we're concave down. So from 0 to 2, we're concave down. And then if I plug 3 in, I get 36, which again is greater than 0. So on that interval, we are concave up. So from 2 to infinity. So we've got everything we needed. We have the intervals for concavity and our inflection points. That wraps up example 2. And now we can move into the last topic and then our last example. So, this next topic is the second derivative test. We're going to start it off with theorem 3.9, which we title the second derivative test. We're going to start off by saying let f be a function such that the first derivative of c is equal to 0, and the second derivative of f exists on an open interval containing c. Then we can say two things. The first one, if the second derivative at c is greater than 0, then f has a relative minimum at the point c f of c. We can also say if the second derivative at c is less than 0, then f has a relative maximum at the point c f of c. And we continue by saying if the second derivative at c is equal to 0, then the test fails. That means f may have a relative maximum could have a relative minimum, or it might not have either. In such cases, you can use the first derivative test, which we looked at in the last set of videos. So now I've got one last example to show you. This is example 3. We're going to find the relative extrema of the function f of x equals negative 3x to the 5th plus 5x cubed. So the first thing we're going to do, we're going to find f prime. Find the first derivative. So the first derivative of this function is going to be negative 15 x to the 4th plus 15x squared. Now we're going to find critical numbers. So we're going to set this equal to 0. So 0 equals negative 15x to the 4th plus 15x squared. Both terms have 15, negative 15 we're going to bring out. And an x squared. So 0 is negative 15x squared times x squared plus 1. And actually, I made one mistake. It's not going to be plus 1. It's going to be minus 1. So set both factors equal to 0. Negative 15x squared equals 0. And x squared minus 1 equals 0. With the first one, the only way that's going to equal 0 is if x squared is 0, which means x is 0. I can add 1, and I'm going to get x squared equals 1. And by taking the square root, I'm going to get x is equal to both a positive and a negative 1. So I've got 3 critical numbers. I've got negative 1, 0, and 1, which means we're going to plug those values in for f to figure out the points where our max and mins could happen. So we're going to find f of negative 1, f of 0, and f of 1. So these are going to be relative extrema. F of negative 1, if I plug that into the original function, I'm going to get negative 2, which means we have an extrema at the point negative 1, negative 2. That's not an interval, that's an actual point. If I put 0 into my function, I'm going to get 0 back, which means another point. We could call these points of inflection are at 0, 0, negative 1, negative 2. Now if I put 1 in, I'm going to get back 2, which means I'm going to have another point at 1, 2. So I'm going to make myself a table. In fact, we're going to go on to another page because before I make that table, we are going to need to find the second derivative of our function so we can test for the sign of that derivative at each of these points. So f prime, as a refresher, was negative 15x to the 4th plus 15x squared, which means our second derivative is going to end up being, we bring 4 down and multiply that by 15, so negative 60x cubed plus 30x That's our second derivative. So what I'm now going to do is I'm going to make a table where one row is going to be the points we found on our last slide. So we're going to have -1, -2, we're going to have 0, 0, and we're going to have 1, 2. So we're going to determine, are these points a min, a max, or neither? So we need to figure out first the sign of that second derivative. So when we take the x value from the point and put it into our second derivative, is it greater than or equal to 0? If I took -1 and put it into my second derivative, I'm going to get 30, which is greater than 0, which we can conclude. So my third row is going to be a conclusion. The conclusion at the point -1, -2 is that we have a relative minimum. If I put 0 into my second derivative, it's going to equal 0, which means in this case the test fails. It's not a min or a max. And then if we find our second derivative at 1, we put it in, we're going to find that we get back -30, which is less than 0, which means at the point 1, 2, we have a relative minimum. So we found our relative extrema. We've got a relative min. Oh, and I wrote the wrong thing in this second one. This is a maximum. Relative minimum at -1, -2, and a relative maximum at 1, 2. And that's going to wrap up this lesson on concavity and the second derivative test.